Good afternoon, everybody. Welcome back to the afternoon session. It's my pleasure to let Veronica start with her third lecture.
Thank you. Okay, so yes, I still put here on a side our overall plan and here what we have seen so far. So we have this ODE, this family of differential equations that we would like to solve. The first day we saw how to build this formal solution, phi tilde A, using the Poincaré method, and I also discussed what the Borel-Laplace sum of this solution is, and this will be the phi without the twiddle because it will be analytic. And yesterday we have seen instead method C, so the Laplace method, which means just take an ansatz as a Laplace transform, and we have seen a theorem that tells us, well, we can in fact find a solution of our equation, which is an integral equation, phi lambda, of the following form. And I don't know if you had questions from yesterday. Maybe I should just make a comment about this space here. So here there is the bullet, but in fact, if one goes through the proof, you see that it doesn't really mean that this phi lambda is on all HL infinity space. There is a sort of threshold capital lambda, and from that threshold on, of course, you will be in all this infinity space because they are embedded one into the other. So since yesterday someone pointed this out, I want just to clarify it. Okay, so the goal of today is to show that the two analytic solutions, so phi lambda C and phi lambda IA, are in fact proportional. And so let me just state the theorem. So this is like in theorem 4.4 in the reference there. So for every lambda root of P, phi A of lambda, Z is proportional to phi C. Okay. And this proportional, remember, is because, again, the equation is homogeneous. So sometimes, so we can here pick up a constant in the power series part. And here, in a sense, I'm implicitly taking as a constant 1 because of this normalization here. Also, remember also that this solution here is unique, in fact, as we showed yesterday, as a consequence of the fixed point method. Okay, so how do we prove such a result? And I will just make a diagram. So again, if you want to go through the detail of the proof, then I will refer to the reference, but I will just give you an overall idea. So we have our ODE in the frequency domain, and so where do these two solutions live? Let me start with the analytic one. So we have phi lambda C, which is a solution of the ODE. And let me also make a division, which in fact will reflect the division of the table between analytic formal and frequency and position. So let's start with the vertical one. The other one that we construct, in fact, is phi lambda of A. So this is a formal solution. Okay. So we have two solutions, formal, sorry, here there is a twiddle, formal versus analytic. And as I was saying, as we already discussed, of course, we cannot really compare the two of them, but we know how to go from formal to analytic using the Borel-Laplace summation. So here, this is Borel-Laplace summation. And I'm doing it like this because, in fact, once I discussed the Borel-Laplace method in general, we have seen, I didn't really prove that this solution was Borel-Laplace summable and, moreover, a solution of the ODE. In fact, I will just recall briefly what is the paradigm of Borel-Laplace summation and where are the difficulties to prove this. So more generally, we know the result is true because of other results, but what I would like to show today is that we can somehow prove this, that this makes sense using a different path. So let me just make a recap, maybe I can do it here, about what Borel-Laplace does. So the first thing is that, okay, you start formally, so this is just Borel-Laplace. This is your formal solution. The first step is the Borel transform. This is formal, so you can always take the Borel transform, and this gives you a germ of analytic function at the origin or in a different point. And then the first difficulty is to resum the series. So this is like sum, and this happens in the Borel plane. So this is the first step that one has to be careful. And also once, so maybe here, this is formal. Let me just do it. Okay. Formal, this is analytic. But even once you understand that you can take the analytic continuation of your function to produce an analytic function phi, here you have to take the Laplace transform. And the Laplace transform along some direction, in fact, require even more. It's not just being analytic, but this is an integral transform. So I just recall it here. Remember the Laplace transform with this notation. Okay. So here there is another check you have to do. And this will produce you phi. And this will be analytic, remember, in a certain half plane, which depends on the direction theta. So in fact, analytic in what I call h theta. So there are, and this is Borel-Laplace. So we can start from the right corner and definitely take the Borel transform. So this will be our phi lambda capital Z. And as I said, so since this, zeta. Since this function is defined in this way, from the property of the Borel transform, what we get here is in fact in zeta lambda, tau lambda minus 1, and then it's a convergent power series in this variable, but due to this fractional power here, it will be defined. In fact, I will draw something that is, you should think of it as a Riemann surface where this is well defined. So let me just here add a branch cut for this fractional power. And I will draw like this, meaning it has a finite radius of convergence. So this is, now here the origin is not, is lambda in fact. So, or maybe let me just write, this is the, I choose as natural coordinate zeta lambda. So this is in fact 0. So this function is convergent inside this disk. And this is just from the definition. This we can always do because it's formal. On the other side, we also, by definition essentially, we know that this solution here, in fact, comes from the Laplace transform of what I called phi lambda. And again, as it's written there, phi lambda is in this set. So in particular, let me just recall what omega lambda was. Again, this is zeta lambda. So here I have the origin with respect to this. And remember that I have to remove some sector. And then, there might be other points that one has to exclude, which corresponds to other root of the polynomial p. So the domain here was this. So this is omega lambda. And this point is missing as well. So this function is analytic here with that behavior, and this function is only convergent in this disk. So what, and moreover, this phi lambda is also, I mean, the way in fact we proved it was analytic and has this particular behavior was using the integral equation. So from here, I can just remember that there was an integral equation in the variable zeta lambda. So here is always zeta lambda. And this is also a solution here. Okay, so you might see already some similarity between, in fact, this true solution, which are given precisely by this behavior. So you see that this has this singularity here, and the other one has also this behavior. Maybe let me just use. But one of the main differences is that they are analytic in two different domains. I mean, the main problem is that this a priori is only analytic in a disk, and the other one instead is analytic in a much larger domain. So what is typically difficult is, in fact, to understand how to extend this solution. This is the first point here. And you might imagine what could be the analytic continuation of this function. But how do we prove that this, in fact, extends analytically even outside the region of convergence? The strategy is to use the fact that on the position domain, we have more regularity. So we have this integral equation, and we have an existence and uniqueness result for our phi lambda. So here is where really we draw the other line, and where working on the position domain make our life easier. So what do we do? The first thing, as you might imagine, is to show that, in fact, this function is a solution of the same integral equation. Because at this point, then we could use the fact that this is the unique one with a certain behavior, which is exactly the behavior like that. So the first thing, maybe let me just draw it here. Sorry. This is just the formal power series. Let me denote by maybe phi lambda, sorry, I put it there. Phi lambda at the sum of the series. So this is just is a different name for the function which is analytic in this sector. This is just a formal power series, but since it's analytic, we call this the sum of the series. But it's only convergent in this disk. So this is convergent in this disk. So the first thing is that, in fact, this is a solution of the integral equation. And why is it true? Because, well, one can check using the property of the Borel transform, which, in fact, you can also go down this way. So in particular, if you take the Borel transform of a formal solution of your differential equation, this function will be a solution of the integral equation. However, notice that here, the integral equation is with respect to this variable. So I'm saying Borel transform, but here I really mean Borel transform and, in fact, a change of coordinate to be on the good coordinate, which is this zeta lambda. Now, we have a solution of this equation, but in fact, the theorem of yesterday tells us that this integral equation has a unique solution in a certain function space. So, step 2 is to use the integral equation as a unique solution in the function space zeta lambda tau lambda minus 1 plus this HL infinity tau lambda, which is in fact what I call phi lambda. Okay, so let's look carefully. We have a solution, but is that so? The question now is, okay, we found another solution. Is that solution of this form? Because if it is in this space, then it's gonna be automatically equal or proportional again up to a constant to this solution phi lambda. So again, what is here we have now this solution, as I said, is analytic in this disk. If we compare, so this is a much smaller region, but therefore in particular we can use the same result also to say that phi lambda of zeta lambda is a solution in HL. So let me just write it here. So phi lambda at is in the following function space. So it has the same behavior, and then this part means just a convergent power series. So I can just write HL infinity tau lambda bullet, but now maybe okay, this disk is called omega near. So let me just write omega near. So why is that true? again, this simply means that you have a power series in zeta lambda to the power n0 to infinity convergent. So in particular, you see that after you take this part, maybe here there is a constant, A0. So after you take the leading order term in front, all the rest will be a convergent power series in zeta lambda tau. So that's why you have tau lambda here. And this space is not only with a certain behavior close to lambda, but also exponentially bounded at infinity. But this set is compact. So in particular, this convergent power series is exponentially bounded inside this compact domain. I mean, once you try to go to infinity. So in fact, this function is there. But therefore, since also, Since also phi lambda without the hat is in the following function space, we have essentially the same, they would agree on omega near, on intersection between omega near and omega lambda. So maybe I can write here the third step. So phi lambda at will agree with A0 phi lambda on the intersection between omega near and omega lambda. Which means in particular that now, since phi lambda we already know is analytic in a much larger sector, once we have that two analytic functions agree on a certain domain, and one is much larger, we can say that, well, phi lambda is the analytic continuation of phi at lambda. So once we are here, thanks to point 3, we can in fact say that maybe, okay. This is proportional. They are proportional, and in particular, phi lambda is the analytic continuation of phi at lambda. Is it clear? Or too fast? Okay, well, but now essentially we have done. Because once we have skipped, so we have found something which is analytic, then we can automatically go up with the Laplace transform. We already know that these admit a Laplace transform, and therefore, essentially, not only we have understood this point, but automatically we have also the other one. So we can automatically take the Laplace transform because we have this bound at infinity, and we are in fact in the good domain for the Laplace transform. This was the whole point of constructing the solution in this way because of the definition. And so once we are here, in fact, we also get that up to this proportionality, we can close the diagram. So we have make sense. We get automatically two things. The first one is that we can Borel-Laplace sum our original formal power series solution. And this is what we have understood more or less at this stage. Plus the fact that since we express the analytic continuation of our germs in terms of exactly phi lambda, then we also get that the two are proportional. Okay, so the whole point to build the solution phi lambda the way we did was precisely to be sure, in a sense, or like a posteriori, to be able to close the diagram in the following way. And the fact that we choose the Laplace transform precisely with this base point lambda was exactly to make this diagram commuting. So that somehow gives us, tells us that choosing a good ansatz also from the analytic side, so directly in the analytic part, we can not only reconstruct the Borel-Laplace sum of the formal solution given by Poincaré, but we can also prove that this solution was already Borel-Laplace summable. I don't know if you have a question about this picture. Maybe I don't know if it was a bit too quick. There is another thing that I want to mention, that in fact, already in the frequency domain, we could have tried to understand whether the two solutions, like the Borel-Laplace, once we assume that the Borel-Laplace sum of phi lambda exists, it is in fact proportional to phi lambda c. And maybe let me just write this here. So if we assume that is Borel-Laplace summable, and we don't want to go to the position domain, so staying on the frequency domain, like can we prove that its sum phi lambda is proportional to phi c lambda? And in order to do that, we really have to think about what they have in common. So what phi lambda and these two A and C have in common. So I've erased them, but it's still on the diagram, so we can try to think about it. Maybe for this it's simpler. So it is defined as, in fact, a Laplace transform. And it's the same also for phi lambda A. So they are both Laplace transform. A priori, we don't know that they are Laplace transform of the same function, so we cannot quite say they agree. But we can take a look at their asymptotic. In particular, using the fact that they are Laplace transform, we know that they have a certain asymptotic behavior. And even if it might be, in general, more difficult to look at the asymptotic, to compare asymptotic expansion, because as I was precisely saying yesterday, you might have different function with the same asymptotic in a certain direction. There are results which tells you, which in fact, if the asymptotic hold in a large enough region, then the two functions are in fact the same. And so, if you compare the asymptotic, well, for the Borel-Laplace sum, we know that the asymptotic is precisely the formal power series we started with. So as I was saying here, we know that we can go back somehow using asymptotics. And this is, in fact, not just asymptotic in the sense of Poincaré, was the notion of Gevrey asymptoticity that I was mentioning the first lecture. So in fact, we really know how, what is somehow the difference between this analytic solution and the truncated sum of this solution here, and is measured in terms of n factorial. So having this control, and in particular if you have it uniformly, gives you some extra control and some extra information about this solution. And in particular, there is a theorem which goes back to Nevalina which let me just state it in a bit quick way. The theorem tells you that if you have an analytic function, so if phi is asymptotic to a certain phi tilde, and this asymptotic is Gevrey and uniform, then I'm not sure if you can read, phi is the Borel-Laplace sum. Is it readable? Otherwise, I can write somewhere else. Gevrey and uniform, and sorry, here something is missing. Sorry, so let me maybe rewrite it somewhere else. I guess I can go here. So what Nevalina tells us is that if you have an analytic function phi asymptotic to phi tilde, where asymptotic means Gevrey asymptotic, and it's also uniform, and in particular also in a very large sector, so Gevrey uniform and in an angle pi sector, then this is the Borel-Laplace transform of phi tilde. Okay, what does it mean? Uniform Gevrey, maybe let me just recall, Gevrey was that phi minus the truncated sum was bounded by a constant, oops, n factorial, and then z to the minus n minus 1. So this was the notion of Gevrey. This is the control you have, and you want that the constants C and A do not depend on Z in a certain region. And the opening angle is the range that you allow for the angle theta. So theta must vary between in an interval, or let's say assume like from minus pi half and pi half. The fact that you need this angle to be exactly of angle pi or larger, it's quite a strong constraint. So usually is what is hard, would make hard to use this result. And in terms of analytic estimate you have to do is not really to prove this bound, which is almost, which is not so complicated, even being uniform, but being of an angle pi is hard because already, like the theorem I mentioned in the first lecture about the Borel-Laplace transform is that typically this gives you an analytic function in an angle pi domain, where the boundary is excluded. So here you really have to enlarge the domain, extend the region to the boundary, and this might be the complicated and technical step. So even though a priori it's possible by comparing the asymptotic, and in particular by showing that phi lambda c is asymptotic to this function in a big enough sector, these require some technical work. So with this approach, we, instead of checking that phi lambda c is asymptotic to phi lambda, to this, to the same solution phi lambda alpha a in a large enough sector, we move to the position domain. And here, the only check we have to do is at least from two analytic functions. So we have to compare an analytic function in a certain domain with an analytic function which is defined in a much larger domain. So somehow let me write an advantage. So even though it's possible not to go to the position, I would say that the advantage of this method okay, so the advantage of working in the position domain is that we compare analytic function and not asymptotic series. Okay. There is maybe another comment that I will make now, and in fact it will be like useful also in order to understand the resurgence, which will appear in the next lecture, is that also from the perspective of resurgence, working on the position domain is kind of the key idea. So already here we might have seen a bit sketchy what is one of the advantages of working in the position domain. And the same will be true for resurgence. So usually working on the frequency domain can be harder, and the position domain has more structure, even though we have integral equation compared to differential equation. But yeah, we gain something. The Borel transform, taking the Borel transform allows us to work with convergent series, and therefore we have a bit more structure, in fact. Okay, so I don't know if you have question about this or comment. I don't know if you have tried to do the exercise for the equation square, our example. So the equation square was here. I don't know if you have tried to take, maybe to check how the equation, the integral equation, which corresponds to the two root look like. In fact, there is another property of the Borel transform, which is, again, related to the fact that we get convergent series and so on, which is the fact that it transforms equation with irregular singularity at infinity in equation which, after you turn them in differential equation, are regular singular at the point lambda, if you use this Borel transform. And again, this is somehow you can use to study certain question about to study certain differential equation with an irregular singularity. If you Borel transform, then in fact you end up studying differential equation with regular singularity that maybe are more easier, or like, yeah, easier to study for different perspective. Okay. So if no question, maybe I will take some time now to discuss the Stokes phenomena, which is, again, one of the property of the solution of differential equation with irregular singularity at infinity. And this will be, again, something we will understand better, or like understand alternatively using the theory of resurgence. So I guess I can erase something here. in our picture here, we still miss B. So I think for A and C now we have done. And tomorrow we will see again what is missing, so how to, in fact, compute, find the solution of a differential equation using resurgence. But this will be very much closely related to the Borel-Laplace summation in a certain sense, so to method A. Yeah.
In your approach, the integral equation, using the integral equation, switching the integral equation, since you are proof that equation is asymptotic sector of amplitude phi. This solution, I mean, is the only one corresponding to that.
Yes, it's the only one corresponding to that. Yes.
So it's better than it's not closed sector, but it's open.
Yes, sorry, yes, I see, yes. I see what you mean. The point is that, okay, I mean, it works only if you take that precise answers, yes. And for that equation, yes. I mean, I think the real, like, one message is really okay. If you manage to take an ansatz which is tailored in a certain way, then you get this type of result. If I take two different, I mean, if I would have taken, for instance, the Laplace transform zeta lambda, if I take the sum of two for two different roots, and then I take, usually when you take the asymptotic, only one of the two matters, and so in particular, you will, I mean, even though they will be, the asymptotic, maybe one sector will be the same as only one, you will not be able to prove the same equality using the result we are doing. I mean, the fact is that you really need to choose one for one specific root. You cannot take some other combination. Okay, so now is we are going through part 3, and this is Stokes phenomena. Okay, so you might have already encountered the Stokes phenomena, again, if you are used to work with this type of differential equation. And in fact, let me now focus on the equation square. I mean, I will not write down explicitly the solution, but I think if you just take a look of how the equation is, if you remember that lambda is a root of p, in this case, p is just lambda square minus 1. So the two solutions are phi 1 and phi minus 1. And this is the only, and this is the only thing I need. So these are the Laplace transform zeta 1, some angle theta. Now, so far the angle theta never played really a role, but it will start playing a role right now. So this is 1 z. Okay. So this is how the true analytic solution will look like. What I just said, I can also drop the letter A and C because we have seen they are essentially equivalent. And okay, and we have seen also that they are in particular Borel-Laplace summable. So if we start with the two asymptotic, these functions are analytic. Analytic where? So let me just make some picture here. This will be our z, and this will be, in fact, zeta. And I will, remember that the way we understand in which domain the Laplace transform is analytic depends on which ray we take. So maybe here, to be precise, I have to add a theta here. So how does it work? first of all, on the position domain, the singularity were at 1 and minus 1. So these are the position of lambda. So we have 1 and minus 1. Okay, and now the domain I was drawing before, this omega lambda, is the domain in which I am allowed to take the Laplace transform. So how does omega lambda look like for 1 and minus 1? So let's do it for 1. I have to remove some region. And then I also have to remove this part. So for 1, so for this one here, the region I am allowed to take is the following. This is omega lambda 1. Which means that every ray which starts from, we can also say from 1 and goes to infinity in the direction theta within this region is allowed for the Laplace transform. And in particular, if we take this one, so if this is my angle theta, here, the solution phi 1 in the frequency domain will be analytic in a certain region, which must be displayed by 1, like to the right, so it will not be an half plane from the origin. And again, it will look something like that. So this will be h theta for the yellow solution. Let me just put a 1, okay. Now, what happened for the second one? So for the second one, the domain is slightly, sorry, this is just 1, not lambda 1. For the second one, the domain will be slightly different because it's essentially reversed. We have to cut away 1. So I will just draw this region in the same way. And then we have to remove this 1 here. So the domain now will be something that looks like this. I hope it's not too messy, but okay. So this one is omega minus 1. And again, I'm allowed to take the Laplace transform along any ray which is in this pink region. So again, in particular, we can take theta in the same direction. Now we will start from here. Okay, and therefore, on the other side, we will have, now it will be displaced by minus 1, so it will be somewhere here. Okay, and it will be like this. So this will be h theta of minus 1. Okay. So these are our two solutions, analytic, and now you may wonder what happens if you start vary the angle. So already from this picture, you can see that there are forbidden choice of theta for the Laplace transform of one or the other. So for instance, if you take a look at, let's look at phi 1. So phi 1 theta of z, we can take, we can vary theta essentially everywhere. The only region we have to avoid is, for instance, the direction pi. So if this ray is horizontal and points toward the negative real, it lies in this region which is forbidden. So for this, for instance, theta equal to pi cannot be taken. So let's say it's forbidden. Because you will be running inside a bad region where the Laplace transform is not defined. Conversely, for the other one, the forbidden region will be the one at 0. Okay, so in particular, this is what tells us that we can extend the region of analyticity of phi1 also across like varying theta in a quite large sector. And in fact, notice that if you start moving this plane, maybe I can make another picture, the analytic solution will glue well together. And you can analytically continue the solution phi1 until you get close to the negative where something must happen. So let me just make some drawing. Maybe first, is it clear what are the problems with this function? So let's first take, again, let's look at both at the same, let's try to look at both at the same time. So if you take, again, 1 and minus 1, maybe first I would say something else. Okay, maybe before doing this picture, let me also mention something. So as I said, these are forbidden, but let's also look at what is the asymptotic of the two solutions. So the asymptotic of the first one, as I was commenting before, if you take the asymptotic along this ray, this will be phi1 of z, and the other one will be phi. This is essentially by definition of the Laplace transform. What is the behavior of these two solutions? The important point to remember is this one. Oops. And then you have your fractional power. So in particular, what really matters is this exponential. If you compare the two asymptotics, you see that they have different exponential decay in different regions. In particular, when you go along the positive reals, this one is the one that dominates, and on the other side is the other one. And this, in fact, you might expect is not a chance. In fact, that is related to the two directions that you see here. What is forbidden for one and what is forbidden for the other one. So if I take, for instance, so for the first one in particular, the action positive reals is allowed. And what you would get, in fact, is if you take as an integral, if you take the integral for the Laplace transform to be the following path, at angle 0 for the first one, you will get a solution which is defined here. And you can also get a solution which is defined for the other one along the negative real. So this will be for phi 1, and this will be for phi minus 1. So this is theta pi. So on this region, you have phi 1, which is dominant. I mean, the other one is the one that would explode in a certain sense. So you discard, and for the other one is phi minus 1. In fact, I'm trying to describe the Stokes phenomena looking, again, in the position domain in a certain sense. But more conventionally, the Stokes phenomena, it's really about the different asymptotic expansion that you have when you approach infinity on different directions. And so here, it's really approaching infinity, going along the positive real. You see this one, the other make no sense by construction. And for the other one is exactly the opposite. The way I'm using the the position domain is because the solution I'm considering are Laplace transform. So I can understand better this type of asymptotic behavior and, in a sense, the Stokes phenomena already at the level of the position domain because the solutions are defined in that way. And so, as I was saying here, there are two solutions separate, but in fact, we can start varying the angle. And if we do that, let's say going along the, so let's just focus on the positive real. We can try to compare the solution like this. So we can take this ray, angle theta, this other ray, let's call it theta plus and theta plus. So we have our two Laplace transform corresponding to this. Let me denote the two solution by phi 1 plus. Maybe I can try to put it down. And phi 1 minus. So let's call phi, we have phi 1 plus and phi minus 1 plus. These are the two solutions analytic in the region that you see in fact here. So maybe this is like theta. Let me just put a plus here. It's more or less the same picture. So phi 1 plus is the one analytic in this region, and phi minus 1 plus is the one analytic in this region. And let's compare. And now let's start varying theta and go across the positive reals. For the first one, there is no problem. So if you deform it below, so let's now take some other direction, theta minus. You see here, I can deform this contour, and for the Laplace transform, nothing is changing because you have this integral transform. You can vary the contour because the thing inside the integral is analytic in this region. You are not crossing any singularity for the solution phi 1. So in particular, we can take the other two solutions, phi 1 minus and phi minus 1 minus. So if I want to make the same drawing here, I have just to take the opposite sector. Maybe it's a bit too much, but this is like theta minus of 1. And for the other one, you have to start here and go the other side. And now I can try to compare them essentially in the region where they are all well defined. So essentially in this region here. Okay. So as I was just mentioning, how do we compare? We said phi 1 and phi 1 minus 1, if I deform this contour, I don't encounter any singularity for my solution. So I can, by analytic continuation, in fact, I can just say that these two will agree on the yellow region. But what happened to the second one? If we start deforming now, we are precisely jumping into the region θ equal to 0, where we cannot take the Laplace transform. So something must happen when you go from here to here for the second solution. And what this picture is telling you is that somehow you will jump in the other solution. So what you would expect is that here you get something. So you may try to relate, to compare the two, but you will be definitely pick up something that comes from the other solution. That's why there is this star, which I'm not making very precise. So there is an extra contribution that comes from this solution, and this is precisely what the Stokes phenomena is telling you. So this contribution here is what is called a Stokes constant. And the direction theta equal to 0, in particular the direction, so for z, maybe I can draw it there. And you see that the ray where this happen is this one. So this is what is known as a Stokes ray, which happen as, so it's essentially z in e to the I, the theta forbidden, so 0 in this case, positive real. So we have, the Stokes ray is where the solution will jump. So here is where the solution cannot be analytically continued, but from the picture we see, I hope we can see that we can expect at least that we will cook up something related to the first one. And this is what is known as a Stokes constant. So Stokes constant, again, I'm not making it precise, but it will be a number, in fact. So, okay, and similarly from the other side. So more generally, what we should expect, so what is this Stokes phenomena and what are the Stokes ray and the Stokes constant? The Stokes phenomena is really the fact that the solution are not analytic, and they are analytic in a certain region, but they cannot be analytically continued everywhere, and there are rays along which they jump, and the jump is what the Stokes constant express. So maybe I just write, okay, maybe I can just add it here. So more generally, if you have a solution of the form I gave you, you have Stokes rays where the argument of 2 root, so for theta equal to the argument of lambda I minus lambda j, where lambda I different from lambda j are the 2 roots of P. And in particular, if you compare solution, and the solution phi lambda I and phi lambda j will jump across the ray, across the Stokes ray. And the Stokes constant measure the jump. Let me just write like this. Okay. In fact, there is a way to see a little bit better how we cook up contribution. And there is also a geometric interpretation of the Stokes constant in this example, but maybe this I will discuss it after the break. And so yes, I hope that in this example where I was using just the solution 1 and minus 1, these theta are clearly the argument of the difference of the 2. So the argument of 2 and the argument of minus 2 respectively. I haven't told you how to compute this number, but this will be probably mostly part of of next time. So I will try to show you how you can, in fact, precisely tell which number is it. In a sense, once you know the solution, the way you would compute the Stokes constant is to compare the two. So once you have explicitly written down what are the two solutions, you can, in fact, compare and see how to compute this constant. But what we will do using resurgence is another way to find out this number. And as I said, there is also a geometric way to compute the Stokes constant, which in a sense reflect a bit this picture. And this is what I will tell you in the next part. So maybe I stop here if there are questions. Still me. Okay. So yeah, I want to say just a couple of words about the geometric interpretation of the Stokes. Of Stokes constant. I mean, I haven't computed anything, but we will see tomorrow morning in the example how to compute this constant. But in order to see, I mean, just to give you an idea of also a different way you can see this, you can compute this Stokes constant, is to take a look at some geometric interpretation, meaning that so far we look at solution of a differential equation, but in fact, and we saw that the solution was expressed in the form of the Laplace transform. But in fact, we can take a look at solution which are again integral transform, but not quite Laplace transform. They are contour integral. So again, just for our running example, the modified Bessel equation. If you take a look at, so if you go to the digital library of mathematical function, in section 10.25, you see this family of equation, in fact, with a much more general parameter. So what there I think is called mu for us was m on n. And if you go to 10.32, you see that you have a bunch of integral solution. Or, yeah. I mean, integral solution, I mean integral transform that express a solution of this differential equation. Some of them, in particular, there is one which is expressed in terms of in the complex domain, is an example of what is known as symbol integral. Or so how these things look like? They are integral, okay, on a certain contour. So this is I of z, where f is an holomorphic map from X to C. Typically, I would say Morse, but let me just say it explicitly. So with non-degenerate critical points. Critical points means derivative of f at the point equal to 0, or gradient of f. I mean, in the example we consider, x is always one dimension, so just xc. More generally, you can take x to be a complex manifold, n-dimensional complex manifold, or also real, I mean also real in fact. But okay, just think about C for the example we need. And what is nu? Nu is a one form, or an n form. So it lies in the, let's just do one, is a one form of x on x. And what is C here, this C is a steepest descent contour. So it means that it's the place, I mean, it's chosen so that this integral, in fact, makes sense, is well defined, and IZ is an analytic function. For certain, in a certain region which depends on Z. So it's analytic in a certain sector. So just to give you an example of something you might have already seen. So if you take now the integral, okay, if you take as a function f the Chebyshev polynomial, Tn of t, and as nu the other one, the other Chebyshev polynomial. So you, both Tn and Um are Chebyshev polynomial, and n and m the same as the modified Bessel equation. So remember, n was bigger than 3, and m was from 1 to n minus 1. What you can check is that this integral, so it depends, of course, of Tn, but let's say for n equal to, more generally, integral of this form okay, now I would say so. Sorry, here there is something missing because I'm saying a one form. Okay. So for suitable choice of contour, integral of this form will be solution of the modified Bessel equation. So these are solution of our equation square. And I mean, and how do you check something like this? Well, it's just taking derivative. And taking derivative, all the, and integrating by part as well. Taking this contour to be a steepest descent contour tells you that in particular all the boundary term will cancel. In fact, maybe I should also say that, I call this a steepest descent contour, but in fact this is an element in the so-called relative homology for X. So I can write it here. So this contour defines a class in what is called the relative homology. What is the relative? So H1, X, and relative to infinity. Okay, what does it mean? You have your map F. This is F. This is the T-plane, which has nothing to do with the Z or with the zeta. And so let's say you take the preimage of plus infinity. It means you take the preimage of a region here. Now, it depends on the degree of F. If F is degree, I don't know, n, you will have some preimage of infinity somewhere. Okay, something like this, for instance. This is the preimage of infinity with the map F. And this contour, so what defines this homology, what define classes in this homology, are contours that connect these different regions. So in particular, this can be one choice of C. There is also something that is typically required, is that the C, in fact, pass through a critical point of F. So, can assume, or like at least I can if this is a critical point for f, so let's call it x1. So if the first derivative vanishes, this will be our C1. That's an option, and it's a non-trivial class in there. If you take something that just connects to region, so a contour like this will be trivial because both end goes to the same region. And there is also another way to think about this contour if you go to the image. And in particular, so the image x1 is a critical point. Oops. And its image under F is called critical value. So if somewhere here I have the critical value, f of x1, a way to define this contour is just to take the preimage of array that goes from f1 to infinity on a certain direction, which direction, let's say direction theta, and this C1 can be defined as the preimage of this ray along F. So F inverse of the ray from F x1 plus E I theta R. This is an F. So the fact that we want to go to infinity in a certain direction is precisely what will tell you that the integral will be well defined because of this exponential. This will be fast decay if you take z to be if you take argument of z equal to theta. So maybe a remark. So the integral is, being well defined, it will depend on the argument theta. So will be for argument of z equal to theta. And if you start varying theta, of course, this region will start moving accordingly. So in particular, you will have, first of all, maybe here I should put some number, 1. So this integral will be defined, you will have one of these for each critical point. And there will be analytic function in a certain domain. Which domain are allowed? The one where this ray is well defined to infinity. And what can go wrong? Well, if you have somewhere else another critical point, so another critical value. So if this is x2, which maps, let's say, here. So if this is f of x2, this direction, no problem, but you might have an issue if you take the direction that contains the 2. So if instead you take a direction which goes through the 2 point, then the preimage of the second one will not be any more well defined because the contour will land in the first one. And so if this originally is maybe something like that, so this is C2. This is a picture for a fixed theta, which is 0 in that case. But as you start varying theta, this contour will start moving, because in fact is the region here at infinity that starts moving as well. And in particular, there are bad theta, as before, forbidden theta, which are precisely the one where one contour will land into the other one. If you have never seen it, maybe it's not super clear, but tomorrow I will show you the example with also an animation. I mean, it's something that you can try to plot as, I mean, if you are used to programming a little bit with mathematics, it's just a command in a sense, or I can also send you the code. Essentially, you can try to. There is also a command which is more or less steepest descent contour, and therefore, if you like, you can try to see. You can, in a simple example, let's say n equal to 3 and no m. So for n equal to 3, you can just consider the integral where you have the third Chebyshev polynomial, which is the following one. So if you take this integral and you will have two critical points. So you have, in fact, two integral here, Ej. You can try to plot. So the exercise is plot Cj. You have two for different direction of theta. And by theta, really, I mean, so what do we mean plot this? Means take the preimage of f, take the preimage under f of this ray for different value on theta and see what happened to this path. Maybe you can also make it move as an animation. So plot this. What do I mean by that one is just take f inverse of fxj plus ei theta are positive. Okay, so theta is this one. And these automatically tell you for which z you get something well defined. So if for some value of theta, this thing is not, you cannot really make the draw of this contour, then this means the function will not be defined for that value of the argument. And what this has to do with the story of the Stokes phenomenon and the geometric interpretation? Well, so solution, integral of this, integral of the, so these are called symbol integral, and integral of this form are solution of differential equation. Morally, the idea is you start taking derivative and you find the relation among them. So symbol integral are solution of ODE. But in fact, not just of ODE. Since you have this exponential here, are solution of ODE with the irregular singularity at infinity. Here, the part irregular, it's morally related to the fact that you have this exponential inside the integral. And not only that, but in fact, the way they are written is maybe not too hard to see. They look almost like a Laplace transform. So this, in fact, I mean, you can prove it, but maybe let me also mention the following. So if you take, you can easily do it in the example, for instance, for this guy. You can see why this thing became a Laplace transform, but it's morally what I'm drawing here. So once I define my contour as the preimage of array, you might think that what I'm drawing there is in fact the position domain. So if we go back to our solution as before, I can just write morally. Okay, so symbol integral. Let me just write our Laplace transform. What does it mean? That if you take your integral, oops. So if you take an integral of this form for some contour Cj, you have to do a change of coordinate. So if you call f equal to zeta, then here you will, let me be a bit sloppy, but you can make it a bit more precise. So when you take the image of the contour, you get one of these line. So you go from 0 to infinity in some direction. So maybe here, let me also add a theta. Here you just get zeta z. And now here, of course, you have to take the pullback of nu. So morally, they are Laplace transform, and you can re-express, or even better, you can just re-express these as nu divided by df in the pre-image of zeta d zeta. Okay, maybe I can just write it in this way. Sorry. So this is what do I mean by their morally Laplace transform of this function. And if you try to do this computation for the example, for instance, this one, in fact, you can compute it explicitly. And if you don't want to do it, you can also take a look at the paper that I was mentioning before, because there is a section full of examples in which computation of this form have been computed also for this example, for the Bessel and other differential equation. So again, these integrals are morally are solution of the ODE and are also morally Laplace transform. So what this has to do, so where does the geometric interpretation of the Stokes constant come from? As I described before, the Stokes phenomena is kind of related to the way these, for different direction of theta, some solution was jumping. So here, what is jumping? Before was the Laplace transform, and now through this equality, what will jump, in fact, is the Thibault integral. So if I just look at this picture, what we see is that if now think of this 2-ray as the 2-ray where you take the Laplace transform integral. If the blue lands on the pink, then, as I was saying, something goes wrong. You don't have this path well defined, and you can compare what happened before and after, as we did before. So maybe let me just remake here the picture. And in fact, maybe let me just make the picture. You should be able to see if you do this example with 4 and 3. So this is the T-plane, which is where this contour lives. In fact, sorry, the Thibault integral, this guy is the Thibault. The contour is the Thibault. And in one dimension, it's not very clear why it's a Thibault. In higher dimension, by higher dimension, I mean if X is higher dimension, they really look like, also called vanishing cycle and so on. So this is somehow the picture. These are Sn-1 if we are in n dimension. And in one dimension, you only have this circle. You don't have the sphere anymore, but okay. So before we have the point 1 and -1. And now we have our function f, which goes from, so this is now zeta. And I'm using what I said here, that we just take the projection f to zeta. Now, the direction forbidden is, as we expected, the one that goes from -1 to 1. So let's go a bit above the bad one. What are the this is degree 3 polynomial, so I have 3 pre-images. of infinity, and since I have this minus sign, this one is at minus infinity. What are the critical points? They are real as well, so they will be here. This is what I will call x1 and x2, and we have that f of x1 is 1 and f of x2 is minus 1. And maybe, okay. So if I take the preimage of one of these contour with this map, and you can really plot it with Mathematica or with something else, you might get a contour like this. And if you do it for the other one, then you will get something that runs in the other critical point. So that's an option. And here, no problem if you are for, so this is the direction theta. So if this was our theta, let's make it. This is the direction theta at infinity. Okay, now you have to imagine that if you start moving theta across, to this blue guy, nothing happened. So this is the one that passed through is the preimage, maybe I should change color, is the preimage of the first ray. So as we noticed before, once you move here, nothing was happened for the Laplace transform, and here will be the same. This contour, you can deform it, taking the end in this region, and it's okay. But for the other one, once you move, you will see that this part flips down. So this part on the back, it's kind of moving, but not much. The point is that this goes down. And so what the picture that you get after, so will be something, again, this not very different. Okay, but so now you see, if I write, maybe let me just do it. If I write as I did before, the difference between the two integral. So remember that before we wrote phi1, phi minus 1 plus maybe, sorry. Let me just use this property here, like property in the sense that I can imagine these as my two contour integral in the first, as my two symbol integral according to theta plus. So I will write them as E1 plus and E minus and E2 plus. What do I mean? Is that this guy is I theta j. So this one is the one corresponding to the blue contour, and the other one is the one corresponding to the other contour. Using this picture, I see what is the jump. So I can compare this with the one below. And again, here, using the same so this equality here is a bit, can be made a little bit more precise, but it's that one. Okay, so the blue didn't change, and this is already something that we were expecting before. And how does the pink change? Well, maybe I can just write it in this way. If the so C2 plus is equal to C2 minus. And then maybe I should put some orientation to decide whether it's plus or minus, but let's say that they're going this way. Sorry, here is. Okay. So this one, if I take the difference between the two, I got a copy of this one. Sorry, I don't know why. So it should be a plus 1 times C1 times the blue one. And so here is what we are going to put here. So the way they change, I mean, you can always flip by a sign, but okay. The way they change, we can see it from the picture, collects one copy of the other contour. And collecting one copy of the other contour, it's morally telling us that the difference between the two symbol integral before and after the jump, see, in fact, the contribution of the symbol integral E1 plus or minus, which in fact did not change in that region. So this is a way so this number here, it really comes from comparing this picture, and it's something that you in a sense can draw in some example, of course not always, but so these things is, okay, like from the symbol. There is another way you can see it, which is already here, and this at least qualitatively tell you where you should expect to see the jump. I mean, I'm making some drawing, but these can be made precise using what are known as Picard-Lefschetz. So, I mean, these really, I'm drawing some contour, but as I was mentioning before, these are really class in homology. And so there is a theory that tells you how this homology class, in fact, jump when you change the direction theta. And this goes under this name, but without giving, I mean, if you want more detail, of course, I can give to you, but let me just. So we have to compare these two pictures, and in fact, the moral behind this story, it's the following. So here is direction theta. You take, you compare theta plus with theta minus plus pi. So you take theta minus plus pi. You take this other direction, and then you see where they do intersect. So the fact that there is an intersection here, it's morally what is telling you that there will be, that the jump will happen here. And similarly the other way around. So either you see it from the picture, or you think in terms of homology class, and therefore you can take a look at how this formula work, and you see how different contours should change. And the fact that they intersect this way is telling you that, sorry, here's, I draw it in the opposite direction, but okay. This will be the jump, not at 0, but along the negative reals. This morally tells you there will be a jump. The fact that they intersect once doesn't tell you that the number is 1. If you really want to get the correct constant, you should compare the contour not in the image. So this is the image which I call zeta, But to get the correct number, you should compare what's going on upstairs. And as an exercise, maybe you can check what is called as modified Bessel zero integral. It's more or less of the same family, but there is one difference, which is that the symbol are not on the complex plane, but on C star. And the fact that you have the C star, so you have an all somewhere, will tell you that this number is not 1 anymore, but will be something else. So you can try to compute here. You can try to make the drawing. And if not, tomorrow I show you how they look like. So for this integral, you can draw the symbol and compute the Stokes constant. And to compute the Stokes constant, you have, so draw the symbol, remember, is taking the pre-image of array to infinity in a certain direction. And the way you will see how many times they intersect, it's through this. So you have to compute the pre-image of array like this and a pre-image of array in the direction theta minus plus pi. And once you compare the two pre-images, you see how many times they intersect. If you do the exercise for this guy, you see that they will intersect only once. If you do the exercise for this thing, you will see something else, and tomorrow I can show you how many times they intersect. But the point is that here, in a sense, you really see that this phenomenon, at least for this class of example, this phenomenon of jumping, it's really related to the geometry or the topology, in a sense, of the of this symbol. Because for this example, let me just make a here the remark is that the function f, which defines this type of integral, is defined from C star to C. And this will play a role. Maybe I have 5 more minutes. No, okay, maybe I should, let me just ask if there are questions and if it's clear how you can compute somehow this number from drawing this integral, looking at this integral and how the different picture intersect. I don't know if it was too quick. It's related to the way they compute, the way this formula works. There is, the paper that I usually look at is by FAM. It's in French, I can send it to you. And in there you see a way to compute the formula. Otherwise, I think also if you take a look at the book by Arnold on singularity theory, you see the same, and maybe that's in English, in fact, you see the same type of formula. But I can send you the reference. The idea is that, these contours are in fact class in a certain homology, and varying theta, you are comparing different base for this homology. And so the jump are described, what these jump are describing is precisely how, this matrix, you should think of this matrix as a change of basis somehow in this homology. You can, in this homology. Okay, so if there are no other questions, tomorrow I will plot this thing. The plan for tomorrow morning is for the first lecture to have just an exercise, and the exercise will be about this example and see how the picture look like in the movie, and so see a pictorial way to compute this. And I will also show And we will also see another way to compute the Stokes constant, which will be more related to resurgence, in fact, because so far, okay, we have seen a more geometric way to compute this number. Before I was, again, more or less arguing what this Stokes phenomena is from the point of view of the differential equation. But in the example, we will also see how, in fact, this number appear more in the spirit of what resurgent functions are. And then in the second hour, instead, I will give a little bit more detail about the theory of resurgence, which it's again related to divergent power series, but since it's very, since divergent power series do not only appear in the context of differential equation, but in fact we can find the divergent power series in other contexts, I will try to give you some example, which will be mostly exercise, and give you an idea of which feature of the resurgent function we can learn looking at, starting from the study of differential equation. That's it, thanks.
Questions, comments?
Yeah. This is Bessel 1/3. I mean, with my parameter Mn, the Mn, yes, M equal to 1 and N equal to 3. U is not there. Sorry, yes, because I usually put UM minus 1, so U0, 1. And this is the third Chebyshev. And in fact, this is not even, it's just another way to rewrite the Airy function. So there is a change of coordinate, and you see I'm using this Bessel, but because the equation is written in the form I like, so when you have the polynomial part, then this 1 on Z, the Q polynomial, and then all the rest. But in fact, there is a family of functions called Airy-Lucas function, which contains also the Airy equation. And after a change of coordinate, this Airy-Lucas function give you the modified Bessel M on N, and in particular, 1/3 is just Airy.
You mentioned we can use polynomial of x point back.
Yeah, it can be. The degree of the equation is related to not the number of critical points, but the number of critical values. So for this, yeah. Also here. Yeah. It's still, it's because for all of them, it's true that you have more critical points. So if you take Tn, it's true that it has n critical point. N plus 1, in fact. But the critical values are always plus and minus 1. So at the end is always degree 2, the differential equation. In fact, the square, so the way the equation, this equation was written, so the equation square was a d square minus 1, and then you have 1 z dz, and then you add this m on n square, 1 on z square. So it's always degree 2.
So we solve the different contours, they give you different solutions for dimensions and everything.
Yes, in fact, exactly. If you instead of taking n equal to 3, you take higher n, what will change is somehow this type of constants. And if you compute them I mean, morally, you would expect to have 1, but if you try to compute it analytically, you find some cosine, what was like of m on n, 2 pi, maybe something like this, or no, sorry, it's 2 cosine. Okay, there is something inside. The point is, if it's 1/3, you should get 1, which is probably 2 because cosine is 1/2. Okay, and in the other example, generically, this is just it's not necessarily 1, and this takes into account the fact that you have more preimage of 1 point. So yeah, there is some relation, in fact.